The apple will act as a trigger. A small copper chain connects the apple to the upper end of the cone. When the apple is lifted, the cone moves and it allows water to flow into the second tank. Under the representation of Heracles, on the diaphragm, a small pulley is installed which allows to adjust the rope. This rope connects the trigger of the hero's bow to the cone. The rope tightens when it's tied to comes out of the hand of Heracles. To prevent it from escaping inside, a loop is formed. It's this loop that allows the user to tense the bow and the rope. Now, when one lifts the apple, the plug formed by the upper cone rises and pulls the cord. This action releases the trigger from the bow that launches its arrow. An additional dimension is added with the presence of sound in this automaton. A hollow pipe is installed. It's hidden inside the tree and goes down to the second tank. During the movement of water, it allows the air contained in the tank to escape. A small whistle is placed at the top of this pipe. The air flowing through helps to imitate the dragon's hiss of pain. After modeling the virtual construction of this automaton, we will now focus on how to interact with them. We consider an interaction where the user performs actions with his hands. This therefore requires the ability to recognize hand gestures in real time in order to trigger an item of the mechanism. Recent approaches for gesture recognition are based on machine learning techniques, and in particular on deep learning techniques. We have considered the state-of-the-art approach of Devino. This method is today one of the most effective in the classification of gestures on the DIDIER gesture dataset database. The hand is represented by a set of 22 hand joints, each represented by its 3D coordinates within a time period that captures the gestures to be recognized. The approach of Devino considers the 66 coordinates x, y, z for the 22 hand joints separately with a time period of 100 frames. Each coordinate, denoted as Ci, is processed using 3 different branches that have the structure of a CNN made of a cascade of 3 1D convolutions and pooling layers. This enables to extract 3 sets of features for each coordinate that are concatenated to represent each joint independently. Then, all the features of the 66 joints are concatenated into a single vector that represents the gestures to be recognized. It's the input of a fully connected layer that performs the gesture recognitions into 14 or 28 gestures. These figures presents an overview of these architectures. Devino's method doesn't take into account the physical relationships that exist between the hand joints, the fingers, at all, and that play an important role in the description of the gestures. Our improvement over Devino approach will consist in taking into account the movement of the fingers. Indeed, during the performance of the gestures, each finger has a precise positions and orientations, as well as specific coordinations of its joints. To that aim, we add a fourth branch of processing that will compute dedicated features for each finger's DI, enabling to capture higher level cues. Each finger is composed by the following joints, as shown in this figure. Joints 1 and 2 that represent the wrist and the palm of the hand aren't used to isolate the fingers. And in the new branch, we have designed each finger, denoted as DI, is processed by 3 2D convolutions and pooling layers. We consider 2D convolution layer since we have 4 joints for each finger on 100 consecutive frames. This is similar to the processing performed by the architecture of Domino for each 1D temporal coordinate signal. Theoretically, the management of each finger should allow a gain of precision in the recognition of gestures. This can indeed capture overall movement features of each finger that represent statistics taken at a higher semantic level. The features extracted for each finger are concatenated together with the output of the dominoes approach and transmitted to the fully connected layer that performs the classification. This last layer classifies the different gestures into 14 categories when used with the DIG gesture dataset. However, the perception neuron suite used to build this new dataset is different from the Intel real sensor. It provides a hand skeleton with only 10 joints, unlike the Intel real sensor that's made of 22 joints. See figure A and B. The model of Domino, as well as our new approach, presented in the previous section, is designed to take as input a hand skeleton of 22 joints. Therefore, to train this model and further classify them, we have to transform the 10 joint skeletons into 22 joint skeletons. To do this, we use a specific linear interpolation with physical constraints to take into account the shape of the hand and the position of the joints. See figure C. To interpolate the coordinates of a missing joint, we consider its two closest neighbors and compute a weighted average. This new method that we have developed obtained a classification rate of 89.97% on DIG. This is slightly behind the approach of Domino that has a classification rate of 91.28%. The standard non-deep learning approach of the SMET obtains a score of 88.24%. However, in the context of the interactive immersive application, we don't need to recognize all the gestures that are present within this database. In particular, after looking closely at the results, we have noticed that for the catch gestures, our method is more effective than that of Domino, with recognition rates of 95.2% versus 94.8%. These gestures, being of paramount importance for the virtual interaction with automata, shows the benefit of our approach that captures the higher level cues of the fingers. In addition, this motivates the building of a specific dataset that contains only the gestures we are interested in. For the purpose of our application, a new gesture database was created in February 2019. This database, called Interaction Gesture Dataset, EGD, brings together two useful gestures for interacting with ancient automata. They have been obtained with the perception neuron motion capture suites. Catch, used to detect when an object has been taken, the combination with the movement of the arm allows to know in which direction the user is carrying the object. These gestures begin with an open hand and ends with a closed hand. Pour is combined with the first gestures. Tells if the user is pouring something, especially when filling a tank. The entire gesture is carried out with a closed hand. The EGD was built by a panel of 4 people. 3 are right-handed and 1 is left-handed. Each person performed the gesture 30 times, which gives 120 executions per gesture. Dataset provides a total of 240 gestures. We plan to distribute this new database on a dedicated website this year. On EGD, a classification rate of 84.26% was obtained with our new approach. The state-of-the-art approach of Domino obtains lower classification rates of 83.57% on this same data. This shows the advantage of having built this second specific database because it specifically contains the gestures that we need to interact with ancient automata and enables us to obtain better results than the state-of-the-art approach of Devino. The use of the design and interaction method within the interactive immersive application makes it possible to obtain an effective and an efficient level of detection of user gestures. When the trigger is activated by the user end, the algorithm performs gesture detection every 20 frames in order to limit the risk of errors by aggregating successive temporal gesture recognitions, and in the worst case, we will have to do the gesture twice so that it will well recognized. A demonstration of the interactive application was led during a public show on April 4, 2018, in front of an audience of 264 people of very varied age. Its purpose was to virtually interact with fellow of Byzantium automatic maid servant to demonstrate it and let the audience understand how its internal mechanism works. This presentation was very well received by the audience, and each automaton is integrated in its context, and the interaction with the user makes it possible to judge the degree of reliability of its reconstructions. The method has obtained good results in terms of real-time gestures recognitions. A classification rate of 90.4% was recorded afterwards on the 50 gestures performed during the demonstrations. In these presentations, we have considered the virtual reconstructions of ancient automata. The approach has required background knowledge both in studying ancient sources and machine learning. The study ancient sources has enabled us to propose the virtual reconstructions of automaton. Machine learning has enabled to provide gesture recognition as a tool for interacting with the designed virtual automata. Linking 3D models of machine with virtual interaction adds an extra dimension to the user experience and enables to appreciate the effectiveness of virtual reconstruction. This virtual immersion revives the thaumaturgy effect of using automata on users. The whole immersive application has been realized under Unity 3D, where the user navigates and interacts in a natural way with the ancient automata. Thank you.
Well, thank you, Jérôme. I guess we can applaud you.
Okay, then for the question and answer, raise hand. Very difficult to see rising hand. You're raising your hand. Have you a question for Jérôme?
Yes, I have a first question. I am a little bit amazed that the interpolation of the joints is actually performing better than having all the data for all the joints. Do you have any hints about it?
I don't. Je n'ai pas entendu. Comment dire pas entendu la question. Can you repeat the question, please?
Okay, so the question is the following one. In your slide number 7, you are talking about the coordinate interpolation, and you are using it. And in fact, what is interesting is that your recognition rate is higher while you are doing interpolation instead of using the 22 coordinates. Does that
Exactly.
mean that in fact we do not need all the 22 coordinates?
Within the interpolation, with the interpolation, I want 20% of classification. It's better with the interpolation.
Right? Is there another question? Raise your hand.
Yes.
Ask your question.
Okay, my next question is about the IGD dataset. Is it publicly
Yes.
available?
Not yet. It's next month. I make this database on a dedicated website to well next month.
Okay, thank you.
Thank you very much. Is there other question? I'll look at a few. If you wish. Someone has a question? Please raise a hand. Raise hand. The public chat. There is a question in the public chat. Can we have the slide?
D'accord, je regarde. I look that.
Slide after the
Yes,
presentation.
yes. I can share the slide after the presentation.
Okay, Jen, you can chat directly with Jérôme, I think, and you send to Jérôme your
send me a private message that that I can you share my slides.
On entend.
Hi everyone, can you hear me? Yeah.
Ouais, moi je t'entends.
Okay, good.
Il y a plein de tests qui disent qu'on t'entend.
Okay, good.
Hi.
So Vincent and I will be talking about lean manufacturing training with VR. So let's start. CESI is a higher education institution that teaches lean manufacturing in several of its vocational training degrees. And as CESI's teaching methods are skill-based and situated, this led to the implementation in one of its training centers of first, and you can see them on the right-hand side of the slide, manual workstations, so that the lean manufacturing students could immerse themselves physically in a simulated production line. And it also led to, and you can see that on the left-hand side, the development of a collaborative virtual reality learning environment with the aim to compare both learning environments. So this presentation will synthesize this project's goals and context, the research protocol that we used, and the results we obtained, and of course we'll eventually discuss these results with you. So first, back to the context and goals of this study. In the field of training, there were previous studies that had already showed that VR training on procedures did allow learners to transfer skills as well as on-site training. However, no evidence yet existed that VR immersion could communicate lean manufacturing concepts as well as physical immersion, which is what this project aimed at analyzing. The manual workstations that were implemented aimed at assembling children's bikes and have the students improve the layout and the process that were left voluntarily non-optimal. So the collaborative VR environment that we based on a specifically designed framework that Vincent will tell you about was developed so that we could compare how working on manual workstations or on the VR simulation might affect students not only in the way they learned the global assembly procedure, but most of all, how they could detect problems and suggest improvements on this assembly line according to key lean manufacturing concepts. And you can see them listed here. They are based on a causal Ishikawa diagram. So problems and solutions in terms of equipment, methods, management, materials, workforce, and environment. So we wish to understand how the two environments, the real physical workstations and the VR environment, affected students in terms of their performance, the number and quality of problems and solutions they detected, but also in terms of experience, how they felt. Vincent?
Yes, it's up to me.
Yeah.
Okay, so first of all, we would like to talk about the framework we have based the scenario on. It allows to define the VR scene and feature of each object in a reusable way. Indeed, in VR scenario, we have so many different objects, and we can't develop a specific interaction and behavior for each object because it will be too heavy to develop. And so we have proposed a framework based on entity, so it represents each object, and on features for entity and interaction associated. So in this way, we can reuse the feature in several objects, so as to make them able to fit together. Suivant, s'il te plaît, Alexandra. So here is how we have developed our framework. It's based on entity, feature, and relation. So entity, in fact, it represents the 3D object with this model. So it can be placed in the VR scene. And each entity can contain several features. And each feature, in fact, describes the object characteristics. So as an example, in the UML class diagram, we've got at the bottom the feature snap oriented and feature slider. And with that, we can say, okay, for this specific entity, we have a specific feature, and here is how it must behave. And for each feature, we can also define the on property and the compatibility property list. So it means that each feature has specific property and is associable with another feature with the compatibility property. It will be a little bit clearer in the next slide. And thanks to that, we can create relation between features. And so we can manage the assembly process. Suivante, s'il te plaît. Okay, thank you. So here is the preview. Yes, it's perfect. Here is the example. So on the right, we have two entities, the entity P360 and the entity load. And on the entity P360, we put two features. I will start with the feature slider. So we have put a feature slider on the P360, and we have put the on property to female lord and the compatibility property to male lord. And so on the bottom, we see the entity lord, and also we put a feature slider on it, and we have the on property is male lord and the compatibility property is female lord. So it's the inverse of the P360. So with that specificity, now the lord can be put on the P360 in a sliding way. So it means that each piece, whatever is 3D model, we can put some feature and make them interactable. And as an example, for the entity P360, we have also put a feature snap oriented on it on the right. So the entity P360, we can put a slide of entity load, but we can also put another piece on the P360. Okay, suivant, s'il te plaît. And in the next slide, we can see that we see the P360, and the user is currently putting a load inside the P360, and we can see that the black port is also another part that have been put with the feature interaction proposed. And okay, that's all. Next step, please. Next, suivant, merci. So with the, sorry, now we need to make all application works collaboratively. So in that example, the two applications at the bottom are in the same room 1, and we need to make them in the same state. So we have based our framework on the photon framework. Peux-tu appuyer une fois, Alexandra? So each time someone is doing something in the first application, the event is dispatched to the room 1. And appuie une fois, s'il te plaît. Next. And once the event is put in room 1, it is dispatched to the both application. And next. And so with that and the feature entity relation proposed, the both applications are in the same state. So several people can interact in the VR scene and work collaboratively. C'est bon pour moi. Suivant. Merci. And so finally, we've got an application where several persons can collaboratively work. They have the same scene state and they are synchronized. And each error made in one application remains in the application of the other user. So with that framework, we can now evaluate how people can learn lean manufacturing. À toi, Alexandra.
Okay, thank you. So as you can see, the design of the research protocol was put together as a collaboration between IT and education researchers, but also together with lean manufacturing experts. And in fact, this protocol consisted in 2 main stages. The first one was, of course, to assess that the virtual environment and the scenario that we had created were actually usable during a real training session. And the next step was to create a mixed research protocol. So we conceived research questionnaires for a quantitative treatment, and these questionnaires included an evaluation of students' performance that was based on the previous causal diagram, and also a qualitative data collection through filmed sequences and interviews. So the physical and VR workstations were all equipped with cameras and microphones. The cohort was quite small. It was a 12-student cohort, and the students were randomly divided into 2 groups of 6 students. The control group worked on the physical workstations and group 2 on the virtual reality learning environment. And in each environment, we had 2 trainees act as operators and 4 trainees as observers. To analyze the data collected, factor analyses were used for the pre and post-session questionnaires. And for the filmed sequences, we used a self-confrontation methodology. The main results from the user experience questionnaire were that, well, first, VR was confirmed as a motivational learning environment. For the whole VR trainees, the session was judged both original and interesting, which was not the case with the real environment students. What was more surprising was that physical workstations were deemed more difficult to use than their VR simulation, and we'll understand why with the next results. The main results of the students' performance evaluation was that the trainees from both environments did identify assembly line problems related to methods, related to environment. For example, the operating procedures that were not clear, the station's layout that was problematic. But the students in the physical environment identified more problems related to equipment or to materials. such as issues with screws, with fitting dimensions, problems with jigs, mounting brackets, basically difficulties handling bike parts and assembly tools. Of course, consequently, and as you can see here on the blue chart, the trainees in the physical environment were able to suggest more improvements related to handling simplicity. Then the main results from the self-confrontations with the film sequences were that we could notice that the assembly process duration was longer in the real environment. It took 70 minutes versus 55 in the VRLE. And the operators and observers interacted more in the real environment. Also, during the self-confrontations, the trainees that were in the real environment spent twice as much time as the VR trainees discussing bike parts and tools handling issues. Then the VR trainees expressed that this absence of physical constraints did allow them to focus more on the assembly procedure. It allowed them to understand how the different tasks followed one another, and they felt they were not impeded by handling difficulties or wasting time on the actual assembly detail, like the trainees in the real world were. So the VR trainees felt and insisted that the VR session allowed them to be more efficient once they carried out the assembly process on the physical workstations. So if we want to summarize these results, we can say that the virtual reality learning environment that we developed first did allow a good comprehension of the global assembly process of the operation phasing. It also allowed a good understanding of problems related to methods. We mentioned the written procedure issues, the procedure phasing issues, and ergonomics issues. However, it did not allow trainees to fully grasp the real physical difficulties that the operators in the real workstations would encounter due to the voluntary limitation in the realistic rendering of interactions that Vincent mentioned. So in the next experimental stage, because we're going to go on with this project, to allow for more accurate appreciation of important lean manufacturing issues such as equipment, as materials and handling problems, the VR environment will be enhanced. So first, with increased interaction fidelity, with improved physical simulation and haptic feedbacks. Such improvements should upgrade the realistic rendering of the interaction, and it should help trainees detect problems and suggest improvements. We would also like to address the lack of interaction between operators and observers in the VR environment. So we thought maybe developing avatars of observers might be a good option, because these interactions did help the trainees in the real world address issues they encountered. Then two other things we might look into, personalized trainee support systems, such as a learning assistance tool that would be able to identify learning profiles and thus adapt the field's resources. So we might use learning analytics data and physiological data, such as heart rate and stress levels, combined with deep learning and algorithms to help us improve the environment's adaptation to the individual profiles, which is something we did not do in this first stage. And the last element that we may inquire is if such a virtual reality learning environment could benefit from the adjunction of digital twin simulation data, which could reinforce the VR world's efficiency as a training tool. So in the next step, we'll definitely look into VRLE as a tutoring and reflexive tool, as well, of course, as improve the physical simulation and haptic feedbacks for an improved appreciation of lean manufacturing concepts. Thank you very much for your attention, and if you have questions, we are all ears.
Thank you
very much. I think
So there is a question about, is there a way to access to this documentation? So I don't know if you mean the presentation, or it's Jorge Gomez Carmona.
Study? Oh.
Ah, the study. Okay. Yeah, it's currently published in this conference, so we can, if you want, we can have a private talk, and we can send you the paper. So,
do we see it as a viable training tool in the future? Yes.
yes.
Yes, it has proven to be a viable training tool for the procedure training, and we have seen that it's partially a viable training tool for lean manufacturing concepts. And I think that once we improve the physical simulation, haptic feedbacks, it should be a very viable training tool. Maybe Vincent, you want to talk about the technical aspect?
Yes. For the technical part, you know, my research is about making it easier to create this kind of an environment. So that's what I've proposed. In fact, we can prove that this tool is a good tool for training. And the main, for me, one of the main issue is that it's not so easy to create some VR scene and some training scenarios. So for me, the key point is how to make it accessible for a lot of people that are not developer. Do you see this? Okay.
Oh, can it be generalized to something else than lean manufacturing? Well, probably the key to this project was the cooperation between the IT specialists, education specialists, and disciplinary specialists. So I think that for other professional training that are not in manufacturing, but include procedures as well, yeah, definitely. But the key is to build the whole process with the disciplinary experts. Or do we think it's more efficient to use both VR and physical real life? Students that have used VR as a first step said that it definitely helped them once they were on the physical workstations. So being able to combine both is interesting. But the aim is really to have only the VR. So we aim to have the VR environment efficient in itself.
I've got
yeah, that's for you.
about the time consumed for the development is a problem. For me, it can be a problem about it takes time, and if you want to update the scenario because of a new process or something else, it means that you need to redevelop something. And with the someone is dancing next to me, sorry. You need to take a lot of time to re-update, and the framework we've proposed is about make it easier and faster to update the scenario. And I've got another question about the Innovas ontology. We use a kind of Innovas ontology. We redevelop a model that is more for us more efficient for VR. So a PhD student, he will publish a paper about this new model. So I advise you to follow us about that. I think it will be published during this year. So. A bunch of
Okay, other questions? Please use the public chat. I think the public chat is the very best way.
Yeah,
question.
someone is asking about immersion and presence during VR training and during real life training. We didn't use that kind of tool, but Alexi, if you've got some advice about that, it could be a nice things to study for the next experimentation.
Patrick asks if we changed the roles during the research. Observers and operators. No, we did not change the roles. They had the same role throughout.
Yeah, because the idea it was at the beginning of the training, and the idea is to make people test the process of assembly, and they should give back their what they have detected as an issue in terms of method, material, and so on. So they need to be a kind of newbie. So we can't mix the session, because they will have some kind of answer after the session. So
there's a question about haptic feedbacks. What do you think is missing, Vincent?
Yeah, yes. In fact, as they are handling some parts, and we need to give some haptics about do they put the part in the right orientation and position and so on. So with some haptic feedback, we could have some info about how to really about the handling of the parts. So that's what we are thinking about.